Good evening, everybody, and a warm welcome to the University of KwaZulu-Natal public lecture, the latest one in our series, What Do Scientists Do? Look Inside the Ivory Tower. My name is Tanya Reinhardt, and I'm the Science Center Coordinator of the Science and Technology Education Center here at the University of KwaZulu-Natal. And if you're wondering what my decoration is, it's not my home, unfortunately. So this is how the Geology Museum looks inside the Science Center. So I'll be your host for this evening. Just some housekeeping rules or some Zoom rules. Please make sure that you keep your microphone muted. And also, I'm not too sure, it's always an issue with bandwidth. So I would appreciate if you can just switch off your video as well. And also, please, if you can just ask your questions at the end of the talk. So there will be a question and answer session. So if you can just please wait with the questions. You also can post the questions in the chat function. So we have a chat function that we're going to monitor. Yeah, so if you have a question later on, there is a raise hand function at the bottom of your screen where it says reaction, this little smiley face. Okay, so there's your raise hand function just for later. Right, it gives me an absolute pleasure to introduce our speakers for tonight, Dr. Mayshree Singh and Mr. Thando Nqasha. And I have to apologize to our Zulu speaking colleagues. My Zulu is not very good, so the pronunciation of Thando's last name is a bit problematic. Okay, so apart from being one of our former physics and geology students, Mayshree also has a PhD in surveying and mapping from UKZN. She ventured off a little bit to WITS, but she basically found her way back to UKZN. She now teaches hydrographic surveying and introduction to geomorphology courses at UKZN, as well as supervising postgraduate students. And it was a great pleasure to see her in 2016 as one of our UKZN Wonder Woman in Science, making the stage. Mayshree has 20 years experience in both the research and industry aspects of probabilistic seismic hazard and risk, and she has worked on projects for the nuclear industry, large dams and large power stations. She has also worked extensively in seismic studies for the reinsurance industries. Mayshree is a director of a consultancy called Maya Geophysics that specializes in seismic hazard and risk assessment. Thando holds a master's degree in land surveying, and his main research focuses on the factors that contribute to the damage caused by earthquakes in low-cost houses, something of course very important here in South Africa. And he has done extensive research in earthquake directional effects on the 2014 Orkney earthquakes. His skills include research, guess that, surveying and mapping, GIS field-based earthquake studies. So I'm gonna just read out the title. So what you can expect tonight, let's shake it, or what's shaking. Look at what causes our Earth to move, interesting earthquake research and implications for KZN. And I'll leave the stage to Mayshree and Thando.
Thank you so much, Tanya. Welcome, everybody. I'm still struggling to see if I'm on camera. It's just taking some time.
Mayshree, you can pin yourself. I think that makes life a little bit easier for you.
Pin, okay, pin myself. Okay, lovely.
At least we can see Thando. Thando?
I'm not sure why my camera, or maybe I've got the other camera on. Okay, let me just close.
We can see your screen now.
Okay.
Okay, super.
Okay, it'll probably take some time to load. Just give me 1 minute, Tanya.
Sure, Thando, if you just want to unmute yourself and tell us a little bit about yourself while Mayshree is still sorting out her issues. What made you study earthquakes?
Hello, Tanya. Hello, everyone. Hope you're good. You see, back in after the 2014 earthquake, a team of UKZN students were accompanied by Karachi. They went in to investigate damage. And after I reviewed those damages, and then I said, oh God, like I saw like the devastation that the earthquake can cause on low-cost houses. And then I wondered if maybe I can do something to assist in the design of the low-cost houses. And that's created for me. That's when I started getting interested in it. And then as I reviewed more factors, like I would say damage, and then I'll try to track the pattern. And then as I'm doing that, that's when I'm getting more factors. Even my study about the directional effects came from that Orkney earthquake study.
Okay, I think Mayshree is ready. So Mayshree, we're going to leave the stage for you.
Okay, sorry, Tanya, I see my camera is not working. It's not behaving. Probably it'll come on just now. Okay, welcome everybody. Thank you everybody for, sorry for the trouble getting started. Thank you for taking time out this evening to sit with us. I would like to extend a special welcome to our distinguished guests, Prof. Modi, Prof. Mustafa, and Dr. Kambelwa. Also welcome to my colleagues in the land surveying program. We look forward to speaking with you, and there will be time for questions afterwards. It's a wonderful opportunity to showcase our work today to such a huge audience. When Tanya and Sally invited us to talk, we jumped at the opportunity. It is a great pleasure to be able to communicate our research to you with the hope of, one, educating the general public on the historical earthquakes in the region, and two, raising awareness on the ways that we can improve resilience to the devastating effects of earthquakes. I would like to introduce you to my colleague. Okay, Thando has already introduced himself. So Thando, please go ahead again. We've rehearsed this, so it has to go according to plan. Go ahead.
Good evening, everyone. Thank you for attending this exciting talk. A special welcome to the land surveying students. It is a great pleasure to be in this platform today. I look forward to introducing my research as I've just given you a brief of what I'm doing. And I'm looking forward to interacting with all of you who are interested in learning about earthquakes and factors that contribute to earthquake damages.
Okay, just a little bit for background. I think Tanya has already summarized our backgrounds. And yeah, so my interest is in the field of seismic tectonics, which involves looking at the causes of earthquakes from a geological and geophysical perspective. Okay, Thando, I don't know if you want to say something.
All right, thank you, Singh. I was a student here, and I'm proud to say that I'm coming from the land surveying department. I am now working on my PhD. I'm also a lecturer at the land surveying department in UKZN and the contract site major geophysics. My interest in earthquake came about when I saw, as I've explained, came about when I saw the damage that were caused by the 2014 Orkney earthquake in low-cost houses. And my PhD study will be looking at the factors that contribute to earthquake damage in low-cost houses. So that's probably where my interest in earthquakes came about. Over to you, Mayshree.
So here's a summary of the talk. In this short time, we won't be able to explore everything in great detail. You will have our contact details at the end, and you can send us an email and we will gladly respond to your queries. We will provide a snapshot of the activities we are involved in. We will focus on earthquake research. We will look at what are the causes of earthquakes and some terminology. We will look at historical earthquakes in South Africa and KZN. We'll also, Thando will explain his research on the directional effect of earthquakes. We will also look at the Haiti earthquakes. That's making news at the moment. And we'd like to end by saying how you can contribute to our research and towards earthquake resilience. So part of the advert for this talk was to enable you to look inside the ivory tower, which is, the way I understand it, looking into the type of work we are doing. So I'm teaching the Introduction to Geomorphology course, which is in the land surveying department, which it enables students to have a working knowledge of the rock types, landforms, and geology maps. I also teach the hydrographic surveying module, which involves learning about underwater mapping of the seafloor. Thando also provides support, teaching support for these modules. Students that come out from these modules develop an interest in the field and choose to undertake postgraduate research at honors, masters, and PhD level. One spin-off from the hydrographic surveying module is the Underwater Heritage Mapping Project, where we use a multi-beam sonar scanners to model in 3 dimensions submerged objects on the seafloor. We also maintain our own UKZN seismic station. And our research is very useful to society and industry. So in our private capacity, we conduct probabilistic seismic hazard assessments for designers and engineers of large public infrastructure like dams and bridges. Yeah, so as you can see, this is a collaborative effort. So here you see this GIF showing that teamwork is involved in order to get things going. Okay, so here's a picture of our students attending field trips in Mgeni Valley, Howick Falls, and Midmar Dam. And these are field trips that are offered as part of the Introduction to Geomorphology and Hydrographic Surveying modules. These trips expose students to the natural local environment. These photographs show the students at the campus swimming pool testing the multi-beam scanner. The Underwater Heritage Mapping Project is funded by the National Lotto Trust. This picture on the left shows Thando testing the underwater camera. Here, Sanele Mkunazi is on camera, showcasing the Blue View multi-beam scanner. Here we have myself with Mr. Chilufya and Dr. Akambewa at the postgraduate symposium. And here Spila is assisting Thando with lowering the Blue View scanner into the swimming pool. And here we have Mr. Forbes and Stephen. Stephen is also a postgraduate student working in, here they're setting up the equipment. We also support students to attend diving courses. Here, Sanele is with the diving instructor, Brian. So they go out to Alawal Shoal and Raggy Cave to extend, they undergo the diving course at the swimming pool and also at the sites in Alawal Shale and Raggy Cave. You can see it's quite exciting. In this slide, we have pictures of data collection and processing of the shipwreck called the Odd. So it's one of the National Heritage Sites that we want to add into our database of underwater heritage sites. We have Sanele here. We are being assisted by Gaino from Subtech to collect data. You can see on board we have all of the equipment. So we can conduct the scans and process the data and view the scans at the same time. So the multi-beam scanner is used to create a 3D image or 3D model of a submerged object. So what we did here was we put in an aluminium recliner into the pool, and you can see the image of it. So we also want to take photographs, underwater photographs of it, to create a 3D model. So what is the use of this kind of work for earthquake research? So we want to extend the skill to offshore mapping to understand what's happening on the seafloor. Okay, so here is pictures of our earthquake investigations. You can see on the left here, we have a picture of our instruments in the seismic station. We have Mr. Roof Botha from Hatrao training Thando on the use of the equipment. Here we have our students, Bila, Ashmi, and Thando at outside near the Bongwana fort. Okay, here we're doing investigations after the 2019 earthquake. Here we have Dr. Akamberwa, Roof, and Thando outside the seismic station. This is at the ESCOM Smart Grid building on Westville campus. Here our team is attending the CGS conference at the CSR Convention Center. We have in the center, we have Ashmi and Thando outside the newspapers after the 2019 earthquake in KZN. Here, these two pictures are at the University of Pretoria. We have the team, Zinat Karati, MSc student, with her team investigating the damage from the Orkney earthquake. We assisted by Sibonelo Zulu from the Council for Geoscience, and she's accompanied by one of our students, Elena Choku. Now let us focus on what kind of earthquake research we do. It can be broken down into a number of activities. We collect earthquake data from a number of different agencies like the Council for Geoscience, the ISC, and USGS. After a large earthquake occurs in the province, we conduct interviews on how the earthquake was felt and investigate and record the structural damage, if any, in order to view and process patterns on what are the causes of an earthquake. We also modify specialized toolboxes. And so in order to look at the causes of earthquakes, we need to look internationally at similar tectonic environments as well. Okay, so Thando is going to explain about the causes of earthquakes.
Thank you, Mayshree. So all of those who do not have any knowledge about earthquakes, I'm going to just provide a brief terminology of earthquakes and the terms that are usually used in earthquakes. So an earthquake is caused by the release of stress underground. The stress is released in form of shock waves that generate outward from the earthquake epicenter. There are many scales that are used to measure earthquake. One of the most well-known scales is the moment magnitude. It measures the moment energy released by the earthquake. It is obtained by analysis of wavefront generated at the seismic station. The stress originates from stressors generated in the earth crust due to tectonic plate motion. Millions of years ago, tectonic plates were at the different positions than where they are currently. With all this large-scale motion, there is pulling, pushing, and friction effects on the tectonic plates. Large amounts of energy are needed to move the plates, and when the rock reaches breaking point, then the stress stored in this rock body is released in form of shock waves. The African plate is moving in the northern direction at a speed of about 1 millimeter per year. Next slide. So earthquakes with high magnitude releases more energy. This leads to stronger ground acceleration and can result in high levels of damage. As you can see, this scale is a logarithmic scale. From this figure, you can see that we have higher occurrences of small size earthquakes. These may occur on a daily basis, and they have negligible effects on damage observed in buildings. While larger magnitude earthquakes which occur, which have lesser rates of occurrence, cause far more damage to infrastructure and result in loss of lives. The large earthquakes that we have in South Africa are in a region of about magnitude 6. This magnitude earthquake will occur roughly like 150 times in a year worldwide. But the energy release is still equivalent to the energy released by the Hiroshima atomic bomb, so it can be quite destructive. Next slide, please. From these diagrams, you can see seismograms of well-known earthquakes that occurred around the world. From these, we can see that no earthquake is ever the same. It depends on many factors. Also, the damage that occurs as a result of earthquake depend on many factors. These factors may include depth of an earthquake, geology of the site, the amount of stress that is accumulated and released, and the distance of the buildings from the epicenter. The 1971 San Fernando earthquake of magnitude 6.4 lasted about 60 seconds, killing more than 64 people and causing over $500 million in damages. The second one is the seismic trace of the 1985 Chile earthquake. This earthquake had a magnitude of 8, and it lasted 10 minutes, killing 77 people and injuring more than 2,500 people. Over 85,000 houses were damaged, and about 1 million people were left homeless. The third one is the Northridge earthquake with magnitude 6.7, and this earthquake lasted 10 to 12 seconds. The death toll for this earthquake was 60, with more than 9,000 injured. In addition, property damage was estimated to be between $13 and $50 billion, making it one of the costliest disasters in US history. For South Africa, we have a good seismological monitoring network, and it is maintained and managed by Council for Geoscience and Academic Seismic Network. Here is a figure from a paper that we published in South Africa, Journal of Geology, with regards to the earthquake of 2016 that happened in offshore in Umhlanga. As you can see, red blocks show that stations that had picked up the earthquake. This is not the case with the earthquake that occurred in 17 June this year. This earthquake was undetected. The coverage in the KZN area is not so good, so we can't pick up the smaller events that are occurring in the faults in this region. As Dr. Singh mentioned before, we do have a seismic stations, and it has been since put in the academic network in 2020.
Okay,
Over to you, Mayshree.
Thank you, Thando. South Africa is considered an intraplate region with relatively lower levels of seismicity compared to, for example, areas in the north, like parts of Mozambique that have high levels of high magnitude earthquakes due to the East African rift system. This is due to the fact that most of South Africa is situated on a large, stable Archean craton called the Karpal craton. Earthquakes occur mostly on pre-existing faults. Two types of earthquakes can be distinguished for the country. That is, those occurring in the mining regions, and the rest are of natural origin, like the Ceres cluster, the Cape Town cluster, Lesotho, and Koffiefontein. There are many other local clusters that are not shown here in this diagram. In order to understand our hazard and risk for the region, we need to look back into the historical record. And the well-known Ceres Toolbag earthquake caused loss of life and damage to property. It was felt around the country. We will show you the trace of the isoseismal map just now. After this earthquake, instrumental monitoring gained a lot of momentum. This is the famous picture of the collapse of a block of flats in the Welkom area after the magnitude 5.2 earthquake in 1976. Fortunately, no one was hurt in this incident. Two of the largest mining-related seismic events in South Africa occurred on 9th of March 2005 in Stilfontein and on 5th August 2014 near Orkney. Thando will explain more about his study there. Both these events were located in the Eastern Northwest Province gold mining region. The events had magnitudes of 5 and 5.5 respectively. Both events caused damage to several buildings, and for the Orkney event, there was one loss of life. Thando, do you want to explain the scale?
Thank you, Mayshree. So there are several methods of determining whether there was an earthquake or not. So one of it is investigating the intensity. Investigating intensity involves asking people what they felt, and also observing the damages that we observe during the earthquake. As you can see, this is the modified Mercalli intensity scale. It describes damages based on level 1. You have level 1 till level 12. Level 1 means that no damage was felt, it was felt by very few people and in favorable circumstances. This may mean that you were in a very tall building and you felt the shaking, or you are very sensitive to shaking. And level 12 means total damage. Usually that's when you'll see big structures who will be totally collapse. Over to you, Maeve.
We will now show isoseismal maps that we have available for past earthquakes focusing on KZN. But I think we will first start with showing you the isoseismal map for the series Toolbag earthquake. Okay, so I'm just we're going to come back to the slide, but I think, Thando, you're going to share your screen now. I'm going to stop sharing.
All right.
I think we're going to first look at the series Toolbag isoseismal map.
All right, so this is the series Toolbag earthquake, which occurred in 1969 and measured a magnitude of 6.3. As you can see from this seismal map, closer to the source, you have higher intensity. You can see that here, this source was somewhere around here. And then closer to the source, you observe higher intensity. This instance may also result in damages. So, and as you are moving further from the source, your intensity decreases, which means your earthquake becomes weaker, and it is not felt as strong as closer to the epicenter. Mesh, can you please describe the earthquake that occurred in KZN relative to seismic activities and the faults?
Yeah, I just want to add here now. We must remember this earthquake happened in 1969. So, when we think about hazard and risk, we must think, okay, at that time, there was a certain level of development. So when we think about what is our risk today, we need to project the same isoseismal map onto our current infrastructure. So those are the lines that we need to think about, and that's why we go back to the historical record. Okay, so now let's move to KZN, Thando. So we're going to start with the 1932 event or earthquake. Yeah, 31st to 10th. So what we're going to try to do is we're going to put our fault database on for that region. So these are the well-known faults in the area, the new tectonic, the faults that are known to be active in terms of generating seismic events. So this is the 1932, 31st December earthquake. You can see at the epicenter, we have a magnitude, it looks like a 7 there. So the source was probably offshore, and it was felt as far as Harry Smith. You can see the last intensity value is intensity 4. So if you remember the intensity scale, it was, I think 4 was some level of damage and everybody felt it. Okay, so we can put that off, and then let's look at the next earthquake. So 12th January 1936, you can see at the epicenter. So this source also looks like it's coming from maybe Port Danford. There's also a lot of seismic events originating in the Swaziland area. So remember, not all, we have not mapped all the faults. We are just putting the faults that we know of. So there could be faults that are there, which we have not mapped. Okay, so we have at the epicenter, we have intensity of 7, and this isoseismal map reaches as far as Harrismith. Okay, and we can associate probably the Port Danford fault or some source in Swaziland to that earthquake. Okay, we can move on to the next one, Thando. We'll put that one off. And we've got the 10th February 1938. We're moving a little south now. Again, similar possible source, the epicenter. I think we've got the numbers here. It must be 4 in the epicenter, intensity 4, probably associated with this fault or some source in Swaziland. 1st November 1942, I think now we're going a bit south. Okay. So we also see the Tugela fault, also a big, one of the faults that are responsible for springs, and it's where springs are located, and we have a number of earthquakes that are located on the Tugela fault. Okay, so the 1st November 1942 earthquake, you can see at the epicenter, we have intensity. Can you see the intensity there? Intensity 6. Right, and then the possible sources for this earthquake is Bongwana. This is the Amanzimtoti fault, and then the one just below is the Bongwana, the CO2 producing fault. Okay, so this fault is also the one that we suspect is the cause of the earthquake that we observed. I'll give you the date just now. Okay, it was, I think, last year. Yeah, so you can see this is one of the big events. It was felt as far as past Lesotho, and I'm not sure what's the last intensity value here. Okay, so the next one, Thando, is 5th October 1986. Okay, I can see Rian is asking about what are the estimated depths. We're looking at about 5 to 15 kilometers. Okay, 5th October 1986, another big one. Intensity 6. So when I say big, I say that this earthquake was felt very widely, right? So possible source, we could say maybe a source in Lesotho, so we think the Sedibal fracture zone. Okay, it's not very clear, it's quite distant from a number of the faults, so we can just assume. We don't have much more information. Okay, another notable earthquake is the 29th September 1989. Okay, yeah, this one as well. Okay, so intensity 6 at the epicenter, felt quite far away, maybe up to Maritzburg. Possible source, the Sedibal fracture zone. In my opinion, I would have thought it would have been the source for this is Bongwana, but I think you can see it's quite close to Sedibal. Yes, I think that's the key evidence or the information we wanted to show you. I think if we can just summarize that again. Thando, can I share now? Is that all that we wanted to show? You've got the seismic events on as well, right?
Yes, yes.
Okay. Yeah, so the seismic events are on as well. There you can see in green. And I think the bigger events are plotted in orange.
All right. Darcy, can I add something?
Yes, go ahead.
All right. It is also important to note that you see, even though in KZN, like you don't get these big seismic events, but then now, like the earthquake causes ground motion. So if an earthquake occurs somewhere here, you see you've got a big one here, and also you have a big one here. So all these will have an effect on KZN, as you can see from these intensity lines. But even though it didn't happen directly inside KZN, but then it will get an effect in KZN.
Okay, thank you, Thando.
Okay, back to you, Mayshree.
Okay, so the possible sources that we've outlined for these earthquakes are the Bongwana Fault, the northeast-southwest trending faults, the Tugela Fault, offshore faults, some sources in Lesotho and Swaziland. So here's an animation from earthworks showing the movement of the tectonic plates. We can see that you can see there's the time period here. So this movement has occurred over millions of years. And you can see as these continents moved apart, there was fractures that have been developed. So on the, in KZN itself, you have a lot of northeast, southwest faults. And we find a lot of the seismic events being located on these faults. And the mechanism, we call that release of stress along pre-existing zones of weakness. Okay, so what we've done here now is we've just listed the isoseismals again, and we've put in the possible sources, as you can see here. We just want to include, just talk about two more. I see on the chat there was one question about another earthquake that we felt here in KZN. So the Bongwana Fault, yes, that one happened in November 9, 2019. And then there was one in June 2021. There was a lot of hype about it. It was felt, I think it was felt strongest near Pietermaritzburg, but it was undetected by the national network. So we're still investigating that one. What else? Okay, so here's isoseismic map. So this is the Sundumbili one on the left, 16 June 2015. And on the right is Mapuranga and one of my former students created isoseismic maps for the 6th February 2016 earthquake. So you can see that the source was probably somewhere offshore. One important thing that came out from this survey and this investigation is that the low-cost houses in the area felt this shaking very strongly. So we see in both cases, and even Thando will show as well in his study, that the low-cost houses are really vulnerable to even small levels of shaking. Okay, so those are the things we want to say there. Okay, so this is a picture from Victor Mapuranga's publication in South African Journal of Geology. He explored the 6 February 2016 earthquake, tried to look at the source of the earthquake and what it's telling us. So all these red dots are the seismic events of different magnitude. We've got 4 plane solutions here of some events as well. What else? Okay. So you can see the epicenter of the 6 February 2016 earthquake and the epicenter of the 1932 series Toberg earthquake. Okay, so it's a summary of the possible sources in KZN. We can see there's the offshore sources, something happening in Swaziland, the Tugela Fault, northeast, southwest trending fault, there's the error there. the Bongwana fault, and some faults associated with the Lesotho cluster, which is Sediville, and the Lilani faults. So, I mean, what does the geology, the geophysics tell us about what are the causes of earthquakes? The geology, the regional geology doesn't give us much in terms of what are the causes of earthquakes. You can see the historical events, which is plotted in red, have much less accuracy in terms of their location. And the instrumental seismic events are plotted in green, which are probably the locations have much more accuracy, but they're telling us the same things. You can see they're concentrated in the same similar areas. In terms of the geology, doesn't tell us much. In terms of the regional geology doesn't tell us much in terms of what are the causes of earthquakes. But if we strip the layers, the sedimentary layers, we know that we've got this very stable carpal craton, and that is where we have, that is the reason why we have lower magnitude earthquakes. Okay, and between the carpal craton and the Namakwa-Natal province is where we have the Tugela fault, and along this fault is where we have a concentration of springs and earthquakes. What else do we know is here's the faults being plotted from a publication from Thando. We've got some information about what's happening offshore, not much. Yeah, we can see that faults, earthquakes are concentrated along this region, occurring along faults, pre-existing faults, pre-existing zones of weakness. And we have clusters here. We have seismic events along the known Bongwana and Toti faults. So what I want to say is that the faults that we have plotted are not the new tectonic faults. So we still have a long way to go in terms of plotting active faults in the region. We need a denser network of monitoring stations in order to get fault plane solutions, earthquake depths, and in order to monitor the smaller events. And then we can find out exactly which faults or which sources are causing the earthquakes. So here is, so with all this information, we can still establish a level of hazard and risk for the region. So we can produce something called probabilistic seismic hazard maps. So here are some well-known publications for the country. We've got Professor Andre Kiko, Dr. Mitzi. They also published seismic hazard maps. We've got a map here from Pagani. Sorry, I was meant to put the dates on. So we can look at the KZN region, particularly. We can look at the hazard there. The way you'd read this is you'd look at, this shows you maps of probability of exceeding certain levels of acceleration. For example, for a given site on the map, we can work out in, say, 500 years, what is the acceleration that can be exceeded at 10% probability. So these kinds of numbers are useful in design. So for the KZN area, in this map, we can be looking at accelerations of 0.1 to 0.15 G. In the mid-sea PSHA map, let's move this a little bit. For this area, we're looking at accelerations of 0.01 to 0.02 G. I think it's this guy here. And in the Pagani map, this here corresponds to accelerations of, just help me get Thando, of 0.02 to 0.3 G. Okay, so this brings us to Thando's discussion on the directional effect. This is a very important skill that he has developed, looking at how the building, how the orientation of the building what are the effects of the orientation of the building with respect to the epicenter, and how that orientation will affect how the building responds to earthquake shaking. Okay, over to you, Thando.
All right, thank you, Mayshree. As the information that you obtain from now, I think we all know that there are seismic events, there are earthquakes occurring in South Africa and KZN. So what do we do about that? My main focus was to investigate the factors that contribute to earthquake damage, and I mainly look at directional effects, as the person just specified now. So what is directional effects? So directional effects is the study that look at the structural response of buildings under different excitation angle. Again, another time that you know excitation angle. What is excitation angle? Excitation angle is the angle between the direction of propagation of earthquake and the longitudinal axis of the building. So an earthquake of small magnitude or medium magnitude propagates in form of seismic waves radially outward from the point source. Therefore, the direction of propagation is taken from the direction from the point of interest to the building. So you can see from this diagram that the epicenter, that's your epicenter, and then your direction of propagation is your line from the epicenter to the building. That's your direction of propagation. And the direction of longitudinal axis is the direction of the longest side of the building. Usually these studies are conducted in the labs, and when they do this, they measure the displacement as a response. Next slide, please. So this concept of directional effects was applied in the OPNI case study. The earthquake propagation direction and the building longitudinal axis were obtained from the georeference remotely sensed data, in this case, Google Earth, and some other photos. As stated above, earthquake propagates the direction from the epicenter to the house of interest. So in this diagram, you can see from the epicenter into your houses, that's your direction, earthquake direction. Next slide, please. So following the 2014 Orkney earthquake, several studies were conducted after. The first study was conducted by Dr. Vanganai Mitsi in 2015. Dr. Mitsi investigated the intensity, conducted the intensity survey following this 2014 Orkney earthquake. The 2014 Orkney earthquake was measured, had a magnitude of 5.5, and it occurred in the Orkney area on 5th August 2014. I think most of us felt that earthquake, even though it was quite far, but it was relatively large compared to earthquake that we experienced in this region. So the study that was conducted by Dr. Vangana Mitsi is what we usually do after an earthquake. So whenever there's an earthquake, we'll do and conduct intensity survey. From this figure, you can see that closer to the epicenter, the shaking was felt much stronger. That's why you have the red from the epicenter, and then as you going further from the epicenter, the shaking effect decreases. So in most of our KZN earthquakes, this is also what we observe, that whenever you are closer to the epicenter, you are getting more effect, and then as you are further from the epicenter, your effect decreases. So again, on this earthquake, in 2016, Korati with a team of land surveying students conducted a detailed field damage survey. From the study, they noted a pattern of damage in low-cost houses. This damage included cracks in the windows and door frames, as you can see from this figure, corner cracks and cracks at joints or supports. So these are the damages that we normally observe in masonry structures, mainly in low-cost houses in KZN. So the data that was collected by Korati is the data that I use from my directional effect study. Next page, please. These are the images that were captured during the field visits in the township of Kuma, Kanana, and Joberton. From these figures, we can see we have Zinet Korati, accompanied by Belina Chawoke and Sandile Mkwanazi, and they were assisted by the colleagues in the University of Northern Cape. Next slide, please. Okay, the concept of earthquake directional effects is based on the force based on pressure equation. So from this equation, you know that whenever you're increasing the area that is perpendicular to the force, the pressure increases. So in buildings, this may result in the topplings of the wall of the building wall that are perpendicular to the earthquake direction. We know that the building has a maximum allowable displacement in both X and Y. So if the displacement that is caused by the earthquake acceleration is greater than the building maximum allowable displacement, then the building is more likely to experience damage. From this figure, we can see that if our excitation angle is 0, then we'll have a maximum displacement in the X direction and we'll have no displacement in the Y direction. This will result in the displacement that is caused by the earthquake acceleration to be greater than the building maximum allowable displacement, which may result in damage. And if the excitation angle is 90 degrees, the maximum displacement is in the Y direction. And if this displacement is greater than the building allowable maximum displacement in the Y direction, the building may experience damage. So ideally in this situation, we would want our excitation angle to be between 30 and 60 degrees. So in this case, the earthquake acceleration will be distributed in both X and Y. More often, this will be less than the building maximum allowable displacements. So your building will be less vulnerable to earthquake damage. Another factor to consider is the location of windows and doors relative to the epicenter. These are unavoidable features that present building critical weak points, and that's where most of the damage starts to occur during an earthquake. Next slide, please.
Thando, am I in the right slide? This one, right?
Yeah, that one. All right. So this figure here just emphasizes what I've just said on the damage on where the damage starts to occur after an earthquake. So from this figure, we can see that the damage that we observed were cracks that were propagating from windows and door frames, our critical weak points. So these are the normal damage that we observe in masonry structures after an earthquake. Next slide, please. Next slide. Okay. So for this study, we categorized the excitation angle into 3 categories. We had 0 to 30, 30 to 60, and 60 to 90. For 0 to 30, we had 2 building short walls that were perpendicular to earthquake, and from 60 to 90, we had 2 building long walls perpendicular to the earthquake direction. And from 30 to 60, we had no walls that were perpendicular to earthquake direction. From this figure, you can see that like the excitation angle of 0 to 30 and 60 to 90 have a higher number of damaged houses. However, we can use this to determine if we can use this to conclude that these buildings were less vulnerable to earthquake damage, but instead we can use the weighted average damage grade, because it may happen that the area has a higher number of houses that had these excitation angles, but the weighted average damage grade will describe the vulnerabilities accurately. Next slide, please. Okay. So from this slide, you can see that for excitation angle of 0 to 30, that's where you have your most weighted average damage grade, which means those buildings will likely experience a damage grade of 60. And for 30 to 60, you have your lowest weighted average damage grade, which is 40. And from 61 to 90, it's a bit higher, which average damage grade of 50. So we can use this now to conclude that the building that have an extension angle that is between 30 and 60 have a lower vulnerability to earthquake damage. Next slide, please. So as we said that whenever you are doing the earthquake directional effect study, you also look at the position of the building critical weak points. So from this figure, we can see that we have we have exposure A, B, and C. Exposure A was when the building one door and one window was exposed to the epicenter. Exposure B was when two windows were exposed to the epicenter, and exposure C, you had no windows that were exposed to the epicenter. So we can see that you have a higher number of houses that were damaged for exposure A. Next slide, please. As I said in the previous slide that we can't use the number of houses to determine vulnerability because it might happen that a certain area has more houses with that variable. However, the weighted average damage grade gives an accurate estimation of the vulnerability of the buildings. From this diagram, we can see that the facing A and facing B have higher weighted average damage grade compared to facing C. So now we can conclude that if there are no weak points that are exposed to the building is less vulnerable to seismic activities. So this study can be used to be applied in the future development of low-cost houses in KZN in particular, to ensure houses that will be less vulnerable to earthquake damage. We did see that we do have earthquakes in KZN. So if these factors can be considered in the design for future low-cost housing development, they may the future houses will, like those houses will be less vulnerable to earthquake damage. Over to you, Mayshree.
Thank you so much, Thando. We also want to conclude with a discussion on the Haiti earthquake. Just a summary of what happened there. So on 14 August, we had a magnitude 7.2 earthquake, where a number of people were killed. And previous to that, a decade ago, we had a magnitude 7 earthquake, which killed 200,000 people. So yeah, so this is a lot of damage was observed here. So here you can see a number of the buildings that collapsed. So if we try to understand what happened, we have Haiti that's situated on an island here. We have it, there's two plates, the North American plate on the top and the Caribbean plate on the bottom, and it's separated by two fault zones. Okay, so this fault zone on the top, its name is the Septentrional Fault, and then we have the Enriquillo Plantain Garden Fault on the bottom. So this Caribbean plate is moving east in relation to the North American plate. Okay, so we have movement of these plates and stress buildup, and that's how we have a number of earthquakes being generated here. So we had magnitude 7 and a lot of aftershocks after that of magnitude 5. So, according to newspaper reports, this fault was the most likely fault responsible for this, the earthquake in 2010 and 2021. And previous to that, in 1751, 1770, and 1860, a number of earthquakes happened along this fault. And these earthquakes destroyed the Port-au-Prince city. And geologists, seismologists are saying that earthquakes are most likely to happen again in the future in that area. Another point is that why do we have so much of damage? It's because the buildings that are designed in Haiti are designed to withstand hurricanes and not earthquakes. Okay, so they can survive strong winds, but they collapse during earthquakes. Okay, you can see the devastation. Okay, so massive destruction of buildings. Okay, so we'd like to conclude with how we feel you can contribute to our research and science. We can, if you'd like, you can donate towards our postgrad students. We need funds for research equipment, field work. You can recommend research focus areas if you find some interesting movement or some fault in your region, some interesting cracks that are aligned, send us an email. We'd like to have a look at it. Whenever there's an earthquake, please complete the questionnaires as accurate as possible. That helps us a lot. If you have a nice remote service site, we really appreciate to use the site for installation of seismological equipment for monitoring earthquakes. And also if you are in the field of design or structural works, always take into account earthquake regulations. If you have any doubts or queries, you're welcome to contact us for guidance. Okay. We'd like to acknowledge these articles that we've used and pictures, figures from these publications. And we'd like to also acknowledge our funders who's assisted us and supported us along the way. Thank you so much, Tanya. I hope we haven't taken too much of time.
No, that was absolutely perfect. You were spot on. Thank you so much for this very exciting and super duper interesting talk. And I'll see from the chat there are gazillions of questions popping up. I'm not too sure if we, so you already answered some of the questions during the event. So if you have a question, if you want to unmute yourself, please just raise your hands. Remember that raising your hands is where reaction is. There's the raise a hands button, and you can, there's a hand coming up already. Chepang, if you just want to unmute yourself and ask the question.
Hi, thank you so much for this. I just wanted to know, somebody answered, but I'm not really convinced about how are earthquakes or hurricanes named, because I just Googled Orkney occurred in August, and she probably thought like, so I'm not sure when are they, how are they named?
Thando, you want to take that?
Yeah.
I think it's a year, place. That's what we usually do. Like it's a year and the place. Let's say Orkney 2014 earthquake. I'm not sure if I'm more to say.
Yeah, I would think so, because I think we do not have that. We do not have like these female or male names that we would assign these earthquakes to. It's usually where if we're associated with the epicenter of where the earthquake occurred. I think that's the way we would be guided towards naming or referring to the quake.
And there is an interesting question in the chat from Sumhuzo Mbona. What is seismology? I mean, like, can you just briefly explain what it is?
Okay. Seismology is the study of seismic waves or signals. I think Thando explained. Thando went through the slide where we have the seismic signals, those wiggles. So a seismic signal is generated historically. I mean, if you have a pin, it used to be a little instrument, a historical instrument on a drum roll. So when there was some movement on the ground, that pen would move and create this squiggle-like thing. So so now in the modern equipment, it's all electronic, and then we have little accelerometers that will move. So, and record deflection of, movement of the accelerometer in the vertical and in the horizontal direction. So we would usually analyze those squiggles or those signals, and that's the field of seismology, but that's just a simplified thing. I mean, we also studied the P wave, and Thando would explain more about looking at, for example, the seismic signal. There's so much you can see in it. For example, when you process it, you can look at the source and how the fault moved, for example. So this seismology is a study of all of that. And it involves geology, geophysics, a lot of different fields to try and understand this little squiggle that we see.
Okay, I think Valerie Singarum has a question. Valerie, if you want to unmute yourself, please.
Hi, thank you for a good presentation. Very, very informative. I just need to please make a request. How about collaborating with schools? I'm a geography teacher. I'm very, very passionate. But unfortunately, the learners are no longer selecting the subject, and creating this kind of interest in secondary schools, I think, is very, very important. So please, if the postgrad students can do these kind of things at a little basic level to actually catch the attention of the learners, I would be so grateful. Thank you.
Valerie, if maybe I can chime in, and Mayshree, sorry. Valerie, we are here at the Science Center. We go out to schools, and we also run like hands-on activities with regards to earthquakes and so on. And we can always liaise with, researchers like Thando or Mayshree to come along. So I'm gonna post my email address in the chat, and if you want to visit, just contact us or contact me directly, please.
Thank you.
Right, and I saw another hand. Is there another hand? Okay, so then there's a question from P. Mokoena. Can earthquakes be prevented from occurring?
And that's a controversial one. I'll leave it to you. Okay, yeah, no. Listen, it's a natural process. So there's no way we can prevent an earthquake. It's going to happen. All we can do is minimize the effects of it, build better, build away from fault lines, build more earthquake resilient structures. So that's the best we can do, because, the well-known saying that it's not an earthquake that will kill somebody, it's more the building. So I think it cannot be prevented. No, it's a natural process, especially the tectonic related earthquakes.
Okay, and there's an interesting question from Taryn. What would be the cost implication of improving low-cost housing for earthquake proofing? Will you or any of your colleagues be looking at cost benefit to motivate for these changes? I think that's a very, very interesting question.
Okay, so there are a few recommendations that Zinat Karati and Thando have put out there. And a lot of it, I mean, and we were just speaking to a colleague the other day, the way the houses are built nowadays, there are a lot of regulations in place. So the inspectors would come afterwards and inspect the houses and approve it. So what we've noticed is houses, people are staying in houses, for example, that are not plastered. So simple things like plastering your house, plastering these houses and then handing it over to the community will make a big difference. So we have made recommendations of, for example, a lot of the houses didn't have lintels, you know, and that's how we observed the cracks forming. There was cracks, from doors because there were no lintels. So those are the little things that we feel that need to be enforced and put in place when passing these houses to the community. So we have made recommendations. As far as costing it out, we haven't done that. I think maybe it would be a job for a civil engineering student. Yeah, but that's an interesting question, and I think it's much needed.
Is there any a show of hands? Otherwise, I can read out another question, or I can ask a question myself. No, I want to ask a question, Mayshree. You know, the houses on the ridge, they are built on Berea sand, and Berea sand usually has an influence on, or sand in general has an influence on the stability, ground stability. So when you look at you know, houses built on rocks compared to houses built on sand, they are far more stable on solid rock than on sand. So how much likely would an earthquake cause something like liquefaction or you know, a tossing of the tall buildings up, for example, on Ridge Road?
On Ridge Road?
Yeah, Ridge Road, or on the ridge, or in Berea itself.
Yeah, listen, liquefaction is would be a problem in the reclaimed areas, so more towards the coast. So so definitely you're right about there would be a stronger effect on houses built on the ridge relative to the houses that are built on the basement rock. Definitely we see that. We see that in the isoseismal maps as well. So you see this relative higher levels of shaking in this kind of areas. Another thing to think about on the Berea sands is we have limestone as well. So we have that kind of risk. So listen, we haven't, for the earthquakes that we've investigated, we haven't seen extensive damage, you know, to our properties. So I wouldn't worry too much.
That's good.
Yeah. So, but definitely you see this relative effect. You would see that.
There's another question. I think we're going to do 2 more questions. If there's anybody who wants to ask the question in person, otherwise I can read them out. There is a question from Isaac Landau, who is going away a little bit away from the shores, from the KZN shores. Can seismic activity under Yellowstone lead to an eruption of the caldera and catastrophic loss of life?
Okay. I've seen that. I've seen that in the news and stories. I can't comment, unfortunately.
Okay, no, not a problem. But maybe you can answer Alistair Clulo's question. Does the size of the 2 tectonic plates moving have an effect on the magnitude of the earthquake?
I don't really understand that question. Thando,
I think what he means is probably maybe if you can explain maybe the length of the fault line or the length of the blocks moving past each other. I think that's probably what he meant.
Yeah, definitely. We see that the longer faults are capable of producing larger earthquakes. Definitely. But then obviously, you know, we have different stresses that are being developed. It all depends on the rate of movement, the amount of stress. So there's a lot of factors that you need to consider when you're looking at the magnitude of the earthquake, of course.
Also, Rian asked you to please post your contact details, please? If you're not, they can always contact me and I can forward the email to you. I think that's probably the easiest. I posted my my email address and also the website, the Science Center website there. Oh, Dr. Sally Frost also has a question. Sally, you want to ask the question yourself?
Hi, Tanya. I was just asking, Japan has such a good reputation for building earthquake-friendly buildings, and they have, I'm just thinking Tokyo, lots of high-rise buildings. What do they do to make them earthquake-friendly? What building practices?
I'm not really sure, Sally, but in general, there's a lot of techniques that can be used for earthquake-resistant design. For example, things like finite element analysis to model the effect of structures, and also reinforcement of structures. So reinforcement concrete structures. What else? And putting making the foundations a bit more flexible. I think those kind of things, and also things like design considerations like soft stories, like avoiding soft story structures. So there's much more stability on the ground level. So those are I mean, it's out of my field, but we talk to some of our colleagues, and those are the things that would help in earthquake-resistant design.
Right. So I would like.
Sorry, Tanik. May I just add to that? Say about 5-6 years ago, when we have had some major earthquakes taking place, the structural foundation is generally very springy. They actually attach kind of a spring mobile foundation for those high-rise buildings. I'm no fundi, but I was kind of curious and I did some reading on it. There will be some kind of structural damage, but the intensity wouldn't be so great. Yeah, thank you.
Thanks, Valerie, for clarification. And I think this concludes the evening. Thank you so much, Mayshree and Thando. Before you're all going to leave, I just want to quickly share a screen and announce our next talk in the public lecture series. So please join us on Wednesday, the 13th of October for another exciting What Do Scientists Do lectures. And this time it's presented by Professor Colleen Downs, and she's the NRF Saatchi Research Chair in Ecosystem Health and Biodiversity in KZN in the Eastern Cape. And the title of her talk is Adapt or Die, the Persistence of African Wildlife in Urban KZN. A look at the why and how of vertebrate species adaptation to urban environments. And it would be great to see you all there. And if you please want to join us, if you want to unmute yourself and give Mayshree and Thando a big, big, big round of applause. Thank you so much.
Thank you.
Well done. Okay,
that
so
was
everybody,
great.
thank you so much for
Thanks,
coming.
Thando. Thanks.
Thank you so much for
Mayshree.
coming, and I hope that we're going to see you all on the 13th of October again. Okay, guys, bye-bye,
Thank you.
and enjoy the
Bye-bye.
rest of your evening. Thanks, Mayshree. Thanks, Thando. Brilliant
Thank you,
talk.
guys.
Awesome.
Thank you,
Thank
everyone.
you.
Bye-bye.
Thank you. Bye-bye.